Hi, Nitty. Wow, we are sad that you are not feeling well. Hope that you are feeling better. Boy, we're having fun with these polar integrals, though. I know that actually scientists have shown that helps you get over the common cold. So we hope that's going to help you get better soon too. So as we look at this, we're going to be integrating this region over this upper half plane between two circles. We were just talking about this. The first circle centered at 0, 0 with a radius of 1. Second one centered at the same 0, 0 with a radius of 2. My goodness, you would not want to do this problem as a type 1 or type 2 region. That would just really complicate matters. So you begin to think, is there perhaps a way that we could look at this problem a little bit differently? And indeed there is. If you begin to see circles, guys, what you can do is say, hey, everywhere where I see an X, I'm going to replace that with R cosine of theta. Everywhere where I see a Y, I'm going to replace that with R sine of theta. And we can begin to work this out. The integrand becomes 3 R cosine of theta plus 4. Now, squaring y would get r squared sine squared of theta. But our dA, from what we just saw earlier, that's going to be r dr d theta. And at this point, we are really dealing in a better situation because our r, we're going to integrate with respect to r first. Guess what those boundaries are? The smallest your radius could ever get is 1, right? You can see we're between the radius of 1 and then the radius of 2, right? R here is strictly between 1 and 2, right? How about theta? Theta is going to be between 0 and pi. And guys, at this point, thank goodness, you're going to be able to really just be able to, proceed and work this thing out. So I'm going to distribute this r in here, and we're going to see where we go. So we'll say we're going from 0 to pi, and here's from 1 to 2. We'll have 3r squared cosine of theta plus 4r cubed sine squared of theta. And then we'll have our dr and our d theta. And at this point, it just becomes, hopefully, a routine double integral. Granted, what we're going to have to do is first integrate with respect to r. What's the antiderivative of a 3r squared? We'll get r cubed. We bump that up to a 3, and we divide by a 3. Cosine of theta is just a constant, isn't it? How about the antiderivative of a 4r to the third? That's just r to the fourth. Look at that. And of course, we're going to have to plug in a 2 and plug in a 1. And, we still have our bounds between 0 and pi. So, I'm going to continue working over here, bring this up, and we'll have our 0 to pi. But as we plug in our 2, we'll have 8 cosine of theta. Plug in our 2 here. 2 to the fourth is 16, so that's 16 sine squared of theta. And then we'll say minus, then we plug in our 1, and we'd get cosine of theta plus the sine squared of theta. And of course, we can distribute that negative and clean this up. Now, it's at this point where, really the multi-aspect of the course is done. I mean, you could have done problems like this last year, of course, and most definitely we can get this to clean up in a hurry. We'd get 7 cosine of theta, and 16 minus 1 would get you a 15 sine squared of theta, and we'll have our d theta. And we could right now maybe just speed things up and go ahead and use our calculator to finish this off. One quick comment, though. I think it's very clear what the antiderivative of cosine would be. We know that the antiderivative of cosine is sine. Sometimes kids hit the panic button a little when they see the sine squared. And when you see sine squared, I just want you to remember, just in case we're going to need this eventually, the sine squared power reduction formula from last year. It's good to just review that a little bit. And you might remember that was 1 minus the cosine of 2 theta all over 2. So we're not going to do that right now, as we finish this up. But sometime in the future, chances are we're going to have to use a power reduction formula, and that could definitely come to our rescue. Whether we're using an 89 or whether we're using a 84, it really doesn't matter. I've got this thing up here, and actually, you know what? Maybe it would be better just to pull up the 89, since we use that, sometimes, and just confirm that, we do have the right mode here, that we are on radians, and we are going to do a second quit. If you hit F3, you go to calc, and you can see we can come down here to integrate. So as we integrate, we could say, well, that's 7. Then we could say cosine of x, that would be good enough. You could say plus 15. Now, what you want to be careful about is for sine squared, guys, you're going to need parentheses around it. You don't have that real nice shortcut in regard to having the squared go above the n. So we've got that right there. That's your integrand. We're going to say we're integrating with respect to x. And I guess we're going to go between 0 and pi is right above that caret. Of course, we have to close the parentheses. So hit enter, and evidently we get 15 pi over 2. So not too bad. Definitely can get this thing worked out pretty quickly. Okay? We doing okay? All right. So you know the name of the game. What's really happening, of course, is anytime we can have some type of a circle coming in regard to our region, we definitely could use that to help us out. Now, this week we're going to get into what we're going to see right here, not just in a polar context, but even in a rectangular. It says find the volume of a solid bounded by the plane z equals 0 and the paraboloid z equals 1 minus x squared minus y squared. Now, a paraboloid is a three-dimensional parabola. And the fact that, you've got these minuses in front right here would indicate that our paraboloid is going to be upside down. So, like we've said in the past, 3D paraboloid, and this would be a circular paraboloid because you can see that, our coefficients in front of x squared and y squared are going to be the same. So it's not quite like a gumdrop, but looking something like that. And, we're going to have this, but of course we've also got the plane z equals 0. So, what can happen is you've got this shape right here, and z equals 0 is the xy axis, of course. And, so you're going to say, let's find the volume bounded by that xy axis and this paraboloid. Well, see, look, if you had z equals 0, you quickly could see that you would be able to get an equation of a curve when z equals 0. And guess what that would be? That would be the equation of a circle. Now, when z equals 0, of course, we're going to say, well, I've got a circle, and I've got a radius of 1. You see, you've dealt with some of these problems last week, and you could think of this either as a type 1 or a type 2 region, couldn't you? This one you could, truly look at in either way. And, I guess what I want to tell you, though, is as you're looking at this region, and, this is what's happening on the XY plane, and we've got that paraboloid above us, and we'd like to find that volume, what you can very quickly do is say, well, I know I'm going to be integrating, and you can see how they write this style out. They'll write an R underneath, and you could say, here's your R, that's your region. You could say, well, I'm going to be integrating this 1 minus x squared minus y squared, and, I'm going to have my dA. And, I'd like to find, that volume that we have here. You could have done this problem last week, for sure. But we could most definitely set this up as a polar integral. And, first, maybe a quick observation. I could factor out a negative from both of the x squared and the y squared. I could get that. And guess what x squared plus y squared is in that link? If we went back to the very beginning here, we could say, well, my gosh, x squared plus y squared is always r squared. Now, could we have broken that down and said that, x is r cosine of theta and y is r sine of theta? You bet you could. But this is such a famous relationship that x squared plus y squared is equal to r squared. Well, you definitely could get that. And then dA, do you guys remember what we're always going to change that to? r dr d theta. And then we're just going to have to say, well, my first integral will be in regards to the boundaries of the radius. So you can look at this region down here. What are the boundaries of this radius? What's the smallest it's ever going to be? 0. The biggest would be a 1. How about theta? Theta is going to span from 0 to 2 pi. And guys, all of a sudden you look at this thing and it is way easier to work this out as opposed to what we saw last week. Here we'd get an r minus r to the third, dr d theta. And, this thing is probably most quickly worked out by hand. By the time you get everything typed in, especially. Look, do some antiderivatives. You get r squared over 2, r to the fourth over 4. Plug in a 1 to a 0. And, really you'd wind up with 1/2 minus 1/4. And, as you work that out, I think we can very quickly determine what that is. It's just going to be 1/4, isn't it? So we'll have our 1/4 between 0 and 2 pi. And then we'll take our antiderivative here. That's 1/4 of theta. Plugging in a 2 pi to a 0. So it's 1/4 times 2 pi minus 0. It's really just going to be pi over 2 at the end of the day. Pi over 2 is the answer that you get there. And if you worked that out last week as a type 1 or a type 2, I'm sure the most frustrating thing was getting like y would equal the square root of 1 minus x squared and the negative form of that also. We doing okay? All right. Now what? Well, R, of course, doesn't have to have strictly numeric bounds. R doesn't always have to be bounded between 1 and 2 or numbers like that. You take a look at such a picture right here, you could say, well, wow, what if the curves in question are, polar equations? What if, the smallest boundary would be h sub 1 of theta? And the farthest away that you could get, the biggest r could ever be, would be bound by h sub 2 of theta. Well, you can see what's going to happen then. You're just going to get those boundaries to show up instead of strict numeric bounds. Okay? So really we just have one last problem to take a look at. It looks like the video is going to run out, but we're going back to a classic BC question. This is actually an old school BC question, one that maybe even would have done on your AP exam. So we're going to pick this up. We're going to have a follow-up video for our last example.